Today, we are going to look at the regulation of the internal environment. So, regulation of internal states. Well, physiological and behavioral systems are responsible for homeostasis, right, which is the maintenance of a stable, balanced internal environment. And changes in the internal environment can affect one's motivation, which is the psychological process that induces or sustains a certain behavior. So the internal states that we're looking at today are going to be thermal regulation, thirst, and hunger. Okay, because one of these things is out of balance, the system needs to come back to homeostasis. And so there's internal mechanisms in place that drive this motivation for us to find food when we're hungry, to find water when we're thirsty, and to find warmth when we're cold. Okay, so let's start off with thermal regulation. So ectotherms get most of their heat from the environment. Okay, these are going to be your reptiles. That's why you'll see them out bathing in the sun. They need that sun to warm up. Endotherms generate their own heat through internal processes. So humans are going to be endotherms. Okay? Both of these are regulated, though, by negative feedback systems. Okay, and they are the primary homeostatic mechanism. It's much like a thermostat that you have at home. So that's why I put the figure on the right-hand side there. Okay. If a desired value, which is the set point, is deviated from, then compensatory actions begin. So if your house goes below the set point, then the furnace turns on. Once it gets past the set point or the set zone, then it's going to turn off. Okay. So the set zone refers to the range of tolerance in a system, but the set point is where things will actually turn off and on. Okay, so that's just an analogy of a thermostat, but what is actually turning on and off in the human body? Okay, so if we look here, you're looking at first the receptors in the skin, the body core, and the hypothalamus, which detect temperature and transmit that information to the spinal cord, to the brainstem, and the hypothalamus, as you see in the figure. Okay? Then, if the body temperature is outside of the set zone, then neural regions can initiate physiological and behavioral responses to return temperature to the set zone. So what might be some of those responses? Well, on the behavioral level, you have shivering, you have heat-seeking or avoiding behaviors, just like you would find heat if you're cold, but you would also avoid heat if you're too hot. Okay. And then physiological responses, constriction or dilation of blood vessels, sweating, respiration, thyroid hormone secretion. These are automatic processes, respiration and sweating and so on, when the body is getting too hot. Okay. And that is how you regulate your thermal system. Okay, moving on to thirst. Okay, so land animals must prevent dehydration or excessive water loss. Now we have to explain a few things here. Intracellular compartment, that is the fluid of the body contained within the cells. So intracellular is inside the cell. Extracellular is the fluid in the space outside of cells, divided between interstitial fluid between the cells, and blood plasma. We also have to understand some forces that drive water movement. For instance, diffusion. So molecules of a substance dissolved in another substance will move until a uniform concentration is achieved. Osmosis is the passive movement of solvent through a semi-permeable membrane between solutions of different solute concentration until both sides become equal. And then osmotic pressure is the force that pushes or pulls water across the membrane. Okay, so let's see how this works, giving you some examples and some diagrams. Okay, on the left-hand side here, you see a little figure, and it says at the top, hypovolemic thirst. Okay, so low extracellular volume from a loss of bodily fluids stimulates hypovolemic thirst. Okay, on the right side, you have a figure, and it says osmotic thirst. So high extracellular solute concentration or very salty fluids stimulate osmotic thirst. Okay, so low extracellular volume, you're losing volume, you're losing it through bodily fluids that stimulates hypovolemic thirst. Osmotic thirst, okay, is from very salty fluids. So the extracellular solute concentration is very salty. So let's look at these each individually. Starting off with hypovolemic thirst, which is triggered again by a loss of fluid volume. Okay, when that happens, you have baroreceptors in blood vessels and the heart that detect a drop in pressure. And the brain also activates responses to this thirst. Okay, the sympathetic nervous system causes arteries to constrict and several hormone systems are activated. After baroreceptors detect the initial drop in pressure, the heart decreases secretion of atrial natriuretic peptide, okay, thereby keeping the blood pressure from decreasing further. Then the posterior pituitary also steps up release of vasopressin, which induces blood vessel constriction and slows the production of urine because you don't want to lose even more. The idea behind hypovolemic thirst is you're sweating it out, you're urinating it out, and so there's a loss of fluid volume. With decreased blood volume, the kidneys trigger production of angiotensin II, and as a result of that, there's increased blood pressure by constricting blood vessels. It releases vasopressin and aldosterone and acts directly on the brain at the preoptic area and circumventricular organs of the thalamus to stimulate thirst and drinking behavior. Okay? Most of what we talk about in here for these different drive states, for thermal regulation, for thirst, for hunger, we're going to be dealing with the thalamus and hypothalamus. Okay, so let's talk about osmotic thirst. Okay. Osmotic thirst occurs when the extracellular fluid becomes too salty. Okay. Eating salty foods can concentrate extracellular fluid. Water is drawn out of cells by osmosis. Loss of intracellular water triggers this osmotic thirst. Okay. So osmosensory neurons and neurons of the organum vasculosum laminae terminalis. That's a handful, OVLT. I'm glad they have an acronym for it. In the hypothalamus, again, we're focusing on the hypothalamus here. Okay? Specifically monitor changes in concentration of the extracellular fluid. Message is then sent to the preoptic area, supraoptic nucleus, and paraventricular nucleus of the hypothalamus, aiding in water conservation. So again, let's look at the figure on the right-hand side because it just puts it into a picture for us. The osmotic thirst is a very, very simple system here. Moving, you see the OVLT, and then that goes to preoptic area. Again, remember hypothalamus, supraoptic nucleus, paraventricular nucleus, water conservation. For hypovolemic thirst, the one that we talked about before, we had the baroreceptors involved. Then we have the brainstem or the subfornical organ. That is a small organ that, again, is very, very close to the hypothalamus. Okay. Then preoptic area, hypothalamic thirst network, and drinking. Okay, regulated again by the hypothalamus. Okay, so now let's move on to hunger, the need for food. So basal metabolism, energy used for heat production, maintenance of membrane potentials, and life-sustaining processes. So we must keep our metabolism up. We need the heat production and the life-sustaining processes with all the nutrients, everything coming into our system. Again, it's going to be under homeostatic control. Nutrients are chemicals required for function, maintenance, and growth of the body. Glucose is also extremely important, being the principal sugar used for energy. Glycogen is glucose stored in the liver and muscles for the short term, a process regulated by the pancreatic hormone insulin. And you see this also in the figure on the left-hand side. When glucose levels drop, the hormone glucagon converts glucogen back into glucose. For longer-term storage, lipid or fat cells, fat molecules, are stored in adipose tissue. Okay? And then lastly, under prolonged food deprivation, fat can be converted into glucose, which can be used as fuel. Okay, so there's a lot of study going on right now about diabetes. You probably see a lot of commercials on TV about diabetes and different medications. So what exactly is it? Well, in type 1, which is juvenile onset diabetes, the pancreas simply stops producing insulin. Okay? So the process that we just talked about is not working. Okay? In type 2 diabetes, this is caused by greatly reduced tissue sensitivity to insulin. So pancreas can be producing insulin, but it's just the process is not efficient in the system. So insulin release is important at meal times and is triggered by several mechanisms. Okay? The first one is the cephalic phase of insulin release, which is mediated by the brain in response to seeing, smelling, or tasting food. Okay? So insulin ramps up, right, even during the cephalic phase, seeing, smelling, or tasting food. Then again, it's released in the digestive phase when food enters the digestive tract. And then finally, again, in the absorptive phase, where you have specialized liver cells, the glucose detectors, signaling the pancreas to release even more insulin. Okay, so let's look at the process here for hunger and the different brain areas. So energy balance, presence or absence of food in the gut, is reported by hormones from the digestive organs. Two hormones important for appetite control are ghrelin, which is synthesized in the stomach and reach high levels before eating and drops after eating, works as an appetite stimulant. So if you follow along on the figure on the right-hand side, you'll see ghrelin at the bottom and a plus sign. Okay, so it's a stimulant. The PYY, released by intestinal cells, reaches high levels after eating and works as an appetite suppressant, and that's represented as a negative sign. Neurons in the arcuate nucleus rely on two types of neurons with opposite effects. Again, guys, we're still focusing on hypothalamic areas. POMC neurons act as satiating neurons when activated, inhibiting appetite and increasing metabolism. The MPY neurons act as hunger neurons, stimulating appetite and reducing metabolism when activated. Okay. And then you also have high levels of leptin, which activate the POMC satiating neurons, but inhibit the MPY hunger neurons, working to suppress appetite. And then finally, all of this is regulated by the hypothalamus and then works on that second order neuron to then initiate the activity or changes in the nucleus of the solitary tract. Okay, so these appetite signals converge on this nucleus of the solitary tract, or NST, in the brainstem. Okay. And this is a common pathway for feeding behavior. Okay, I wanted to throw this one in here also because people are really interested in the effects of marijuana and how marijuana is being used for or the ingredients, the active ingredients in marijuana, I should say, are being used for appetite stimulants and things like that. Okay, the endocannabinoid system is a major regulator of appetite and feeding. Okay, now remember, endocannabinoids are endogenous substances that act like the active ingredient marijuana to stimulate hunger. Okay, so the active ingredients in marijuana are activating an endogenous substance in our system to help stimulate hunger. Now, now we're talking about set points versus positive incentives. Okay, so we start off with the set point. This assumption is that hunger is a response to an energy need. Okay, so we eat to maintain an energy set point. If you look at the graphic on the right there, You'll see hunger gets, let's say after 2-3 hours, you see hunger going up. Then you feed yourself, right? And then the energy reserves go way up, and then you're not feeling the hunger. After a few more hours, you feel hunger, the reserves are going down, you eat, then it goes back up again, except, you know, yeah, and that continues throughout the day. Okay. So the typical assumption here is that eating works like a thermostat, a negative feedback system. It turns on when energy is needed and off when the set point is reached. So just like we talked about with thermal regulation, and I showed you that thermostat example. Okay, so that's the set point assumption. And we believe that that set point could be, again, these are theories, monitored by different mechanisms. The glucostatic theory says that glucose levels determine when we eat. Okay? Whereas the lipostatic theories say that fat stores determine how much we eat over long term, explaining why weight tends to be constant. However, with all these set point theories, okay, they do not account for the influence of external factors on eating and hunger. We are drawn to eat by the anticipated pleasure of eating, and this is known as the positive incentive theory. What this says is that we have evolved to crave food. I don't know if you're like me, but when 11:30, 12 o'clock comes around, I know, well, that's lunchtime. I might not be really hungry at that time, but I'm going to eat anyways. Okay, because that's kind of how we've structured our day. We know if we don't eat at that time, we're not going to eat again until 5 or 6. And so there's a lot of influence by external factors, right, that influence when we eat. So even though there might be some internal monitors there, there's also definitely that positive incentive that plays a role as well. Okay. And so we go on to obesity. All right. And why this, because we've talked about homeostasis, we've talked about set points, and we've talked about the analogy of a thermostat. So why does obesity occur though? Okay. Because if the body is trying to bring back to homeostasis, why do people overeat? Okay. Evolution favored preferring high calorie foods, eating to capacity, storing fat, and using energy efficiently. If you think about this, you know, many years ago, people were hunters and gatherers, right? And they would go out and they would kill an animal that would be very high calorie food. They would eat it to capacity, probably because a lot of it would go to waste if they didn't, right? Then they would store that fat. They wouldn't eat for maybe 3 or 4 days. And then they were also very active. Okay? So that whole explanation does not describe most of us today. Okay? Cultural practices and beliefs promote overconsumption, as we mentioned before in the last slide, with that positive incentive. Okay? So why do some people become obese while others do not? Because there's still all those external factors are around everybody. But sometimes, why does it affect some people more than others? Well, there's energy input differences. Okay, so some people are just eating more high calorie foods. There's the cultural norms. The cultural norms is, again, eat everything on your plate. Don't be wasteful. Any kind of family gathering, it's always focused on food. So those are cultural norms. And then the large cephalic phase, or response to sight and smell of food, okay, might just be very strong in these individuals. Also, energy output differences. Exercise, right? Some people exercise a lot, some people not at all, right? And then diet-induced thermogenesis. Some people are dieting out there, some people do not. And don't forget that genetics do play a role in this. Okay, it's not going to be the end all. It's not that there's one gene that's responsible for this. But we do know that there is a heritability factor here that obesity does run in families. Okay, so what's being done about it? What are some of the treatment approaches for obesity? Well, we have appetite control. So drugs are used to dampen the hypothalamic appetite controller. increased metabolism. So these are what which cause the body's metabolic rate to increase and burn more calories. So increased metabolism is just moving and being active, right? Inhibition of fat tissue interfere with the formation of new fat tissue. Reduced absorption, drugs such as orlistat work by interfering with the digestion of fat. Reduced reward, so here you're dealing with medications, serotonin agonists, right? Drugs that reduce the brain's reward circuitry. And then anti-obesity surgery. On the left-hand side, I gave you a figure there where you can see that has to do with bariatric procedures, which bypass part of the stomach or intestinal tracts to reduce absorptive capacity. But we also know that liposuction is also used, which is a surgical removal of fat tissue. Okay. And then finally, we end with just a couple eating disorders here. Anorexia nervosa is a syndrome in which individuals severely deprive themselves of food. The name of the disorder suggests the patients have no appetite. And that's the reason for anorexia, and that it originates in the nervous system. So that's the nervosa, anorexia nervosa. One of the best treatments is family-based treatment, also called Maudsley therapy, which focuses on refeeding of the anorexic person instead of trying to identify causal factors. There might be lots of causal factors, a lot of emotional damage, a lot of psychological harm being done to this person. But in the short run, what they really need is refed, because anorexia can be very lethal for these individuals. Bulimia is a related disorder in which individuals also believe themselves to be fatter than they are, but periodically gorge themselves and then either vomit or take laxatives to avoid weight gain. Okay. And then finally, in binge eating, people gorge themselves with excess food to the point of illness. All right, thank you.